everyone. My name is Iacovos Kolokasis, and I'm going to present you our ongoing work, SmartSweep, a system for efficient space reclamation in tiered managed heaps. Today, popular big data analytics such as Spark and Flink run on managed runtimes. These analytics demand to process large amount of datasets, so they need large heaps for their computations. But scaling DRAM in a single server is costly and impractical. To overcome this problem, we can use remote memory by using idle memory across remote servers. This is a scalable and cost-effective solution to extend the Java heap today. However, the GC over remote memory is expensive. Let's say by having a large heap over remote memory, where this heap is on remote memory and you will use the local DRAM as a page cache. During the garbage collection and during the scans and compactions, there is a lot of network traffic as the collector needs to access remote objects. So our approach is to divide the heap into two subcomponents. We have a local heap in the local memory and a second larger heap over remote memory. This dual heap architecture gives us the opportunity to cope with large GC costs by limiting the GC operations only in local memory. So no full scans and compactions over remote memory. In the paper, we show that such a design has the advantage to reduce the network traffic up to 177 times compared to a single heap approaches. Now the challenge is how to reclaim space in remote heap promptly. Otherwise, if we don't reclaim space promptly, we can result in out-of-memory errors because the remote memory is limited. Our approach is the SmartSweep. It's a proposal for space reclamation in remote memory without GC scans. We use the two-heap architecture, and we have the local heap and the remote heap. And now the remote heap is a region-based, so we treat all objects as a single unit inside a region. Instead of scanning a remote object, we estimate which objects in H2 are alive. To do this efficiently, we use the metadata in the local server about each region. To reclaim now the dead object in H2, we transfer regions from the remote heap back to the first heap, and we allow the garbage collector to work locally and reclaim this object. So, and next, after we explain the problem statement and the overview of our solution, I'll present you the preliminary design and implementation of SmartSweep, and at the end, I will show you some preliminary but promising results. The first challenge of our design is to find dead objects without scanning the remote heap. For this purpose, we have to estimate the live object for each H2 region. To do this, we track the forward references from the first heap to the second heap, is this with the red arrows. And also, we need to track the changes in the object references inside the regions. For example, an update if the object in the object reference indicate a creating of garbage. For the forward references now, we use a spatial information approach. We see that using a simple reference counting per region result in misleading results. For example, as you see in the figure, in the first region we have 2 pointers that results in object C, and in the second region we have again 2 pointers that results in 2 different objects in the second region. But we have 1 object here and 2 objects here. How we can distinguish these cases? For this region, we use a liveness byte map, where each byte of this byte map maps a 4K segment in H2. So we check where each forward reference lands in H2, and we mark the corresponding byte in this byte map. So now we have the information that 1 byte is active here and 2 bytes are active here. Next is for the inter-region references, we track the updates by the mutator threads. To do that, we use a card table for H2 where each byte maps again 4 kilobyte segments of H2, and we instrument the post-write barriers of the interpreter and the JIT compilers to record mutator updates. At the end of each marking phase, we count the number, for example, in here, and during the update of the mutator threads remove 1 references, and we have this information in the card table, and again, it removes the other 2 references. We have again we track these updates in the card table. And at the end of the marking phase of the garbage collector, we can count the number of dirty cards that reveal changes in the object graph. After finding the live objects in H2, the challenge that we have to solve is how to reclaim dead object without compactions. For this purpose, we need first to score each H2 region. For the scoring purposes, we use the ratio of the number of dirty bytes in the liveness map to the number of objects in the region. Also, we use the number of the dirty cards per region. For example, in here we have one byte in the liveness byte map and 2 dirty cards. So this is better candidate to reclaim it. Then, after we do that, we need to define a threshold that helps us to select which regions we are going to reclaim. To avoid in-place compactions, we select to transfer regions from H2, the objects in H2, back to H1. To do that, let's say we move the object from this region back to H1, we update the reference, and in the next garbage collection cycle, the garbage collector is going to reclaim the NE object, and it's going to move the C object back to H2. For the regions that are fully of garbage, we just zero their metadata, and we have more information in the paper. The final challenge we have to solve is to maintain the cross-region and the cross-heap references to avoid runtime errors due to dangling pointers. An iFix is to move the region's entire transitive closure. However, this is expensive where dependencies are widespread in the whole H2. Another approach is to leverage the property of SmartSweep placement strategy that puts at the transitive closure of an object into a separate region. This provides limited connectivity across region, and it's cheap to patch these references in place. However, for a future work, we want to try to maintain cross-region remember sets that we will update during garbage collection and during the JIT post-write barriers. Our preliminary implementation of SmartSweep is that we implement SmartSweep on top of TeraHeap. TeraHeap is the state-of-the-art dual heap architecture system in OpenJDK 17. We organize objects into region and reclaim, the TeraHeap organizes objects into region and reclaim entire regions where objects are dead. This is suitable for large and low-cost capacity storage devices, but it's impractical for limited remote memory and results in out-of-memory error. Our prototype now moves to H2 only primitive types and leaf objects, and there are only forward references from H1 to H2. These primitive and leaf objects for big data workloads occupied more than 70% of the Java heap, as we see in Spark and Neo4j, and confirms that our prototype captures the dominant memory behavior. Also, we set SmartSweep to access remote memory via NVMe OF and use memory mapped.io. For our experimental setup, we use 3 servers, one server to run the application and the other 2 servers act as remote memory. And we run Spark with 8 mutator threads and Neo4j Graph Data Science, the community version which supports only 4 mutator threads. And we run in all setups with 8 GC threads. As you see in here, we evaluate SmartSweep compared to TeraHeap. Using linear regression, logistic regression, SVD++ and triangle counts in Spark, and SynDLP in Neo4j graph data science. We see that across the execution, SmartSweep achieves comparable performance with TeraHeap, that TeraHeap do not reclaim space promptly and waits to reclaim entire regions of garbage objects. However, the good point of SmartSweep is that it can reduce the space waste by 50%, as we see in this experiment here, where we show the H2 garbage objects before and after each garbage collection cycle. Next, we evaluate how sensible is having a static threshold. By using, in here, in this experiment, we use 4 different thresholds, low value threshold and high value thresholds. And in here, we have the performance breakdown by showing the mutator thread execution time, the major GC time, and the minor GC time. And here is the performance of TeraHeap. By having a small threshold means we move to H2, from H2 to H1, more regions that contains garbage instead of live objects, okay? And we see it here. And the performance, it's comparable with TeraHeap. If we have a larger threshold, we transfer from H2 to H1 more regions that contains more live objects, okay? And this put pressure in H1 in the garbage collector, and we show this pressure mainly in the major garbage collection time and also in the minor GC time. Because the garbage collection cycle becomes more frequent and the garbage collector cannot reclaim enough space. To conclude and to show you the future work, we show that to deal with large GC cost over remote managed heaps, you need to use a dual heap approach. The problem in the dual heap approach is how to reclaim memory promptly. And we show SmartSweep. SmartSweep shows how to reclaim dead objects in remote memory without scanning the remote heap by estimating the amount of garbage and move regions with large amount of dead objects from the second heap back to the local heap in DRAM and allowing the garbage collector to reclaim this object. SmartSweep cuts the wait space by half and stays as just as TeraHeap. For future work, we want to extend SmartSweep to support transfer to H2 object with references and supports a dynamic threshold for selecting which regions to move from H2 to H1. Then we want also to extend the evaluation by using CXL and also show what happens with compressed DRAM setups. Thank you for your attention. I'll be happy to answer your questions.
I have a question.
Okay.
I always have to have a question when there's no question for me. So you mentioned, of course, that your prototype doesn't deal with the references in the remote heap. Do your workloads really need that?
Well, because, okay, for example, if we use, we don't know how these workloads, these big data workloads will change in the future. So a more complete solution should have also this support. And also, if we support the object with references, we might find also other cases beyond big data frameworks that we can use.
Okay, so you're preparing to be more general than the specific workloads that you have at hand, is that right? Yeah, okay, all right, thank you. Any other questions? Otherwise, we can adjourn for coffee or tea or whatever your preference might be. So let's thank the speaker one more time.
Thank you very much.